Welcome to Maths with EJD. In this video, I'll be talking about nonlinear systems and stability analysis. This is quite a bit close to what we did in the previous video, where we talked about phase portrait analysis, where we talked about critical points and their trajectories around these critical points. So here we are taking things a bit further, still in the same line, except for the addition of some new concepts. So nonlinear systems and stability analysis, an overview for starters. Okay, so nonlinear systems, we're talking broadly about systems of differential equations. So that's why we're talking about systems. Nonlinear systems are mathematical models. They're mathematical models where the output is not directly proportional to the input. Okay, so these systems can exhibit complex behavior, like the ones we referred to in the previous video, complex behavior such as limit cycles. Limit cycles are also known as centers, I believe. They can also exhibit chaos. Now, the idea of chaos is coming up, and we have bifurcations. Bifurcation is simply, division into branches as things progress in a dynamical system. So they can experience bifurcations, all right, making their analysis more intricate compared to linear systems. So linear systems are more straightforward than nonlinear systems for sure. So let's talk about stability analysis. We're talking about nonlinear systems and stability analysis, which we already have a bit of idea on. So stability analysis is used to determine, whether small perturbations, that is when you change things a little bit in a system, whether small perturbations in a system will decay over time. That is, if you add a bit of something, will that thing die out over time, or it will lead to something bigger? Will decay over time, in which case you have a stable system, or will it grow, making the system unstable? Okay. Will it grow, making the system unstable, or remain constant? Will it remain constant? In that case, it has neutral effect. Okay. So for nonlinear systems, right? For nonlinear systems, this is often done by analyzing the system's behavior near its equilibrium points. And we did something like this in the previous case, except that this we are going a bit deeper. All right. So we've also seen the concept of linearization. Linearization near equilibrium points. So that's where the idea of Jacobian matrix comes in, or in this case, we can also see the idea of Lyapunov exponent. So let's see how this works. So for a nonlinear system, the behavior, near equilibrium points or what you call critical points that make the system in a steady state. So for a nonlinear system, the behavior near equilibrium points, okay, can be analyzed by linearizing the system, by linearizing the system. Okay, and what that simply means is this linearization, right? Linearization involves approximating, the nonlinear system. Okay, you approximate the nonlinear system by a linear system, which simplifies the analysis. Okay, so with all this said, can we switch over to see an example? Okay, all right. So, um, let's see an example involving nonlinear system, nonlinear system in population dynamics. I mean, my research area is population dynamics overall. So I really love doing work in this regard. So that's where you talk, whether it's in ecology, epidemiology, and even social systems. Okay. So consider the following nonlinear system of ordinary differential equations modeling the population dynamics of two species. Say you have a prey, you have the prey species X and predator species Y. Okay, see how this now goes. You have the X, the T equals X into 1 minus X minus Y. Okay, so you can see X times X here automatically makes this system nonlinear because that's one of the dependent variables. And then when you come to dy dt for the predator, you have dy dt to be y into 2 minus x minus y. Again, y times y is y squared. That also makes the system nonlinear. So here, say where x of t is the population, of prey at time t, then y of t is population, the population of predators at time t. Then we also, yeah, I think now look at these terms. Now the terms 1 minus x minus y and 2 minus x minus y actually describe the interactions. It describe the interactions between the species. It determines the interaction between the species with competition for resources. So they are competing for resources. Competition for resources and predation being the dominant nonlinear dynamics. So I mean the fact again that you have x multiplying y and x multiplying itself. That's competition among similar species. But then having interacting with Y, that's some kind of interaction also, which is like predation of one on the other. So one leading to the reduction of the other. So yeah, so how do we tackle this system? That's the key issue we have to deal with now. So in step one, just like we did in the other video, the first thing is to find the equilibrium points. Find the equilibrium points. Okay. And to find the equilibrium points, what do we do? Equilibrium points are where the system is at rest. Okay. Equilibrium points are where the system is at rest. That is, both dx dt equals 0 and dy dt equals 0. So this means solving the system x into 1 minus x minus y is equal to 0 and y into 2 minus x minus y equals 0. So you want to solve this simultaneously. Now, from the look of things already, all right, if you say for dx dt equals 0, what that simply means is that you take the first part, that is x into 1 minus x minus y equals 0. So from here, you have x is equal to 0 or 1 minus x minus y equals 0. Okay. So we have this, right? For dy dt, so we have this for now, right? In the meantime, we have for dy dt, equals 0, right? That means that we have y into 2 minus x minus y equals 0. Okay, so that means y is equal to 0 or 2 minus x minus y is equal to 0. So we also have this. So what do we do with this information now? Now, because there's interaction going on among them, so we have to combine, we have possible combinations. So one of the combinations is, we have, okay, I'm looking for a very nice way of putting this. All right. So let's imagine that this is x and this is, yeah, this is x and this is, okay. Um, Let me try to see what I want to do. Okay, imagine you have x up here and you have y up here, or better still, let me do it this way. So you have x, you have y. Okay. So for x now, for x is 0. So you have x can be 0 and x can also be 1 minus x minus y. Okay. And then for y, um, okay, yeah, I know what to do now. Yeah. Yeah, this is a better way to put it. So you have x down here and y at the right hand side. Yeah, I think this is better. So you have x is 0 here, and here you have 1 minus x minus y. And then here, uh, you have y. Y can also be 0. Okay, y can be 0. And then you can also have y to be 2 minus x minus y. Or let me even leave this line out. So y can be 2 minus x minus y. So to get your solutions, you need all the possible combinations of these things. So first of all, you can have x to be 0 and y to be 0. You can have x to be 0 and y to be 2 minus x minus y. Here you can have x to be 1 minus x minus y and y is 0. And here you can have 1 minus x minus y and y is 2 minus x minus y. So these are 4 possible results you can get. So for the ones that are done, you can pick them out. Okay, you can pick this out. And for the other ones, you have to solve if there's no clarity yet. Okay, so let's take them in pairs and deal with them like that. So, and that takes us to step 2. So that takes us to step 2, where we find the intersection, find the intersection of the conditions, find the intersection of the conditions. So we have to compare them this way. These are all the four possibilities. So you already have uh uh we have the first one is 0, 0. That one is settled. So that means x is 0, y is 0. Okay. X is 0, x, y. They are critical values, right? That's 0, 0. Done. Okay. So the next thing is, so let's go for which other one? Okay, let's go for this now. Okay. So number 2, we have where you have x, y, where x is 0. You have x is 0 and y is 2 minus x minus y. So x is 0 and y is 2 minus x minus y. So what that simply means is that since x is equal to 0 now, mm, since x is equal to 0, right? Um, okay, I'm trying to see what can we do here. So since x is 0, so that means we have 0 into 2 minus y, okay? And for this also, so y is equal to 2 minus x, right? Trying to see, what do we do here? So x is 0, and then we have 2 minus y. Okay, but of course, for this, I think we also take y to be 0. Let me quickly confirm that. 0, 2 minus x minus y. Solving for y gives y equals 2 minus x. Not in this. Oh, yeah, I think it's here. If y is 0, we get the condition that x is 0 from dx dt equals 0, right? So, um, if 2 minus x minus y is 0, solving for y gives y equals 2 minus x. Okay. Um, in that case, we have to take the value of y, which we already know to be 0, you know. Um, okay. So again, we have 0, comma 2 minus, so this y, we have 0, 2. So that's another critical point now. Another critical point that xy equals 0, comma 2. So we already have the first one where xy is 0, 0. And then we have this one also to deal with. Okay, so we have 1 minus x minus y equals 0. That's number 3. 3 x y. So we have 1 minus x minus y, and then this is 0. Okay, so again, this becomes 1 minus 0 equals 0. X is 0 already. So, and for this case, we also take y to be 0. So that's 1, comma 0. That's another critical point that we have. So we have a third critical point. So we have 0, 0, 0, 2. Now we have 1, 0. So we have the last one, and that would, in that case, we have to solve a simultaneous equation. So you have x, comma y equals 1 minus x minus y against what now? 2 minus x minus y again. That's this fourth one here. Okay, so in that case, we have, so we, okay, I think we keep setting everything to 0, right? So for this one now, 2 minus y will be equal to 0. I think that's what we got to here. So this is more like 2 minus y equals 0, and that is why y is equal to 2 here. So in case you're wondering why this is like this, and the same thing happens here also. So we already know that x is 0, right? So it means we have 1 minus y left to be equal to 0. And that means that y is equal to 1. And that is why we have this last one here. So in this case, too, we set them to 0 apiece. So this is 1 minus x minus y equals 0, and 2 minus x minus y equals 0. Okay, so we have to solve simultaneous equation here. So that this means that 1 is equal to x plus y, and this means that 2 is equal to x plus y. Okay, so if we solve simultaneously, you have but this is some kind of contradiction. By setting x equals 1 minus x, by setting y equals 1 minus x, and y equals 2 minus x, then we can equate them. Okay, let's see what happens. So we have x plus y equals 1, and then 2. I think let's see what we can do with this. So by setting 1 equals 1 minus x and y equals 2 minus x, and we equate the two together, we have okay, clearly here we have more like 1 minus x minus y. We already know this is 0. That means that y is equal to 1 minus x. Done. And then for the other case too, we have 2 minus x minus y equals 0. Okay, that implies that again, y is equal to 2 minus x. So we can equate this two. So it must, we have 2 minus x equals 1 minus x. This is not making sense, I think. So 2 is equal to 1. This is not making sense at all. Right. So what do we do here? Because they're all from up here, right? Each of them is equal to 0. So we can solve them simultaneously. So y is 1 minus x. Y is also this. So does the equilibrium points are 0, 0, 1, 0, 0, 2, and 1, 1. So now this is not making so much sense right now. Let me see, there's something from the system I'm not getting right. So this is 2 minus x minus y. This is 1 minus x minus y. Okay. Okay, I mean, let's take this. I may have to make an annotation later. So here now, if we trying to see, normally it should be more straightforward than this. That's the competition part now. Okay, so normally we should solve this simultaneously. Let's assume that the solution we get is 1, 1. But in a normal situation, you should be able to solve this normally, and you get the values of x and y. So so in this case, if this is so taking so let's take this whole thing to be 1, 1, or if I take all this to be 0, should it be 1, 2? Okay, let me check out the Python code before I return here. We have a Python code to take care of this, right? For the this is okay, I did not do Python code for this. Okay, I've forgotten. So no Python code for this. Okay, so we have to just keep at it. So let's assume that this one is at the end of the day it's 1, 1, which I'm not able to justify now based on this system, which we have from the beginning. Okay, so let's take it that this is what we have at the end of the day. So at the end of the day, we can say we have 4 equilibrium points, so which we have listed already. So we have 4 equilibrium points. We have 4 equilibrium points from everything we've done now. That's one, we have 0, 0. Okay, let me just write all this like this. We have 4 equilibrium points: 0, 0, 1, 0, 0, 2, and then 1, 1. Okay, these are the 4 equilibrium points based on what we have. So the next step we want to take is to linearize. So step 3, so linearization near equilibrium points. We did something close to this in the previous video, linearization near equilibrium points. So I think it may be helpful to start from the beginning again, where we had, what was that? We had the t, okay, equals x into, yeah, here we had the x is into, equals x into 1 minus x minus y. And the y dt is the other one. So we have to remind ourselves of that. So dx dt equals x into 1 minus x minus y. We can call that f1 of x comma y. Or for easier handling too, for easier handling, so we can write this as f1 of x comma y is equal to x minus x squared minus xy. So it's easier to differentiate this way. That's why I wrote it that way. Then we have dy dt equals y into 2 minus x minus y. Again, we can write this as f2 of x comma y equals 2y minus xy minus y squared for easier differentiation. So we can get the Jacobian matrix. So get us on the switch. So the Jacobian or the Jacobian matrix will be this j of x comma y, which is equal to partial f1 partial x, partial f1 partial y, and then we have partial f2 partial x and partial f2 partial y. Okay, in that case, this is j of x comma y equals partial f1 comma x partial x. That's 1 minus we differentiate x here. That's 1 minus 2x minus y. Okay, so here we have 1 minus 2x minus y. Then partial f1 partial y. So this is the only y here. So it means we have minus x in that regard. So this is minus x down here. And then we go to partial f2. So partial f2 partial x, we have x only here. So there we have minus y in that regard. And then partial f2 partial y, that's 2 minus x minus 2y. Okay, 2 minus x minus 2y. 2 minus x minus 2y. So in the next thing we have to do now is to evaluate. Now we evaluate the Jacobian matrix. Evaluate the Jacobian matrix at each equilibrium point. At each equilibrium point. Okay. So starting with 0, 0. So we just go straight. So j of 0, 0, that's pretty easy. Anywhere you see a number, that just goes to 0. So here we have 1, 0. Anywhere there's, yeah, so 1, 0, 0, 2. Okay, we have just 1, 0, 0, 2. So this is 1, 0, 0, 2. So the eigenvalues are 1 and 2. In fact, this is easy to read. You have this and this. So if you have a triangular matrix like this, so the eigenvalues are just straightforward to read. So here, the eigenvalues are 1 and 2, they are 1 and 2, both positive, okay? Both positive, indicating that the equilibrium point, indicating that the equilibrium point 0, 0 is unstable. Okay, it's unstable because we have real numbers, both positive. That's an unstable node. Yeah, unstable node based on the last video. Okay, so that's done. The next thing is we go for the next one. That's J10. These are the 4 now. We have done the first one. We have done this now. So we go for J, which is 1, 0. So X is 1, 1, 0. X is 1, Y is 0. Okay, anywhere you see x, put 1. Okay, so that will be, so in that case, we have x is 1, right? So this is minus, because x is 1, so this is 1 minus 2. So that's minus 1. Okay, x is 1, so this is minus 1 again. Then y is 0, so this is 0. X is 1, so 2 minus 1 is 1. Okay, then this is 0. So we have minus 1, minus 1, 0, 1. Okay, minus 1, minus 1, 0, 1. All right, so we go for that. Minus 1, minus 1, 0, 1. Okay, uh, so in this case now, the eigenvalues, the eigenvalues, this still looks like a triangular matrix. So the eigenvalues will just simply be this and this. So the eigenvalues are minus 1 and 1. Okay. So the presence of a negative and positive eigenvalue indicates that the equilibrium point, that the equilibrium point 1, comma 0 is a saddle point. It's a saddle point, and because of that, it is unstable, which is unstable. Okay, done. Then we go for the next one, J02. So J02, that's the third equilibrium point. So J02 now. So X is 0, Y is 2. X is 0, Y is 2. So we go here again. X is 0, Y is 2. So 1 minus Y, 1 minus 2, that's minus 1. J is 0. I mean, X, yeah, X is 0, Y is 2. So this is just 0 down here. Okay. So minus 1, 0. And then here, Y is 2, right? So with minus 2. And here, X is 0, Y is 2. So that's 2 minus 4. Yeah, 2 minus 4. That is 2 minus 4 is minus 2. So that's minus 1, 0, minus 2, 2. Okay. Minus 1, 0, minus 2, 2. So here we have minus 1, minus 1, 0, minus 1, 0, minus 2, 2. Interestingly, because of this 0, we still have a triangular matrix. So the eigenvalues will simply be this and this, minus 1 and 2, easily. So here, the eigenvalues, wait, this is minus 1, 0, minus 2, minus 2. Yeah, minus 1, 0, minus 2, minus 2. Okay, so the eigenvalues, okay, the eigenvalues are minus 1 and minus 2. So if you follow the normal process, that's what you're going to get. The eigenvalues are minus 1 and minus 2. Okay, both negative, both negative. And if both are negative, they are real and negative. That's a stable node. The eigenvalues are minus 1 and minus 2, both negative, indicating that the equilibrium point, the equilibrium point 0, 2 is a stable node, is stable. That's the implication. It is simply stable. Okay. Then we can have the last one. So we have J1, comma 1 equals. So again, we go back to the basis. So we have 1, 1, right? So this is 1 minus 2 minus 1. So that will be minus 2. Then this is 1 because, yeah, this will be minus 1, of course, because x is 1. Then 1, 1, right? So this is also minus 1. And then this is 2 minus 1 minus 2. That's another 2 minus 1. All right. That's 1 minus 2. That is 0. So that's minus 2 minus 1 minus 1, 0. Okay. So that's also easy because of the 0 down here, we have a triangular matrix. So you can just read off the eigenvalues along the principal diagonal. Okay. So we have J11 to be minus 2 minus 1 minus 1, 0. Okay. So again, the eigenvalues are the roots are the roots of the characteristic equation. Okay. Um, lambda squared plus 2 lambda plus 1 equals 0. Okay. Yeah, let's verify this. Let's verify this. Let's be sure that's correct. So let's do the eigenvalue for that. So we have eigenvalue for minus 2 minus lambda minus 2, minus 1, minus 1, 0. We find the determinant of this equals 0. So this is 0 minus lambda, sorry. So this is minus 2 minus lambda into 0 minus lambda, then minus 1 minus 1 equals 0. Okay, so this is like, so we can have, so, this is minus lambda times minus 2 into times minus lambda plus 2. That's a smart way, because the 0 minus lambda is minus lambda. Then minus can come out of it. So minus 2 minus lambda is minus lambda plus 2. So this is minus 1 times 1 is 1 equals 0. So we have minus cancel, minus and minus is plus. So we have lambda into lambda plus 2 minus 1 equals 0. So we have lambda squared plus 2 lambda minus 1 equals 0. Okay, so that works. So it means we don't buy this based on what we have. Minus 2 minus 1, 0. Okay. So, yep. So it's lambda squared plus 2 lambda minus 1. Right. So, okay, let me just go straight. Lambda is equal to minus b. B here is 2 plus or minus square root of 2 squared minus 4 into 1 into minus 1 all over 2 times 1. So lambda is equal to minus 2 plus or minus square root of 4. 4 plus 4, 8 all over 2 times 1, 2. Okay, so lambda is equal to minus 2 plus or minus root 8. Okay, 4ac. Yeah, root 8 all over 2. So lambda is equal to minus 2 plus or minus 4 times 2, that's 2 root 2 all over 2. So lambda is equal to minus 2 plus or minus 2 plus or minus 2 root 2. So 2 can cancel out, so we just have minus 1. All right. So we have minus 1 plus or minus um root 2. Yeah. So, root 2 is bigger than minus 1, because root 2 is 1.414 or something. So we have, so lambda 1 is simply, okay, this is simply the same thing as minus 1 plus or minus 1.414. Okay. So we have 1 plus 1.414. All right. Or lambda 2 is 1 minus 1.414. Okay. So this is lambda 1, which is equal to 2.414, which is positive. And then lambda 2 is minus 0.414, which is negative. So the eigenvalues are not both negative, right? They are not both negative. They are both, one is positive, one is negative. So this this shows this shows that the equilibrium point, 1, comma 1 is also a saddle, right? One is positive, one is negative. It is a saddle, which is unstable. So which is also unstable. Okay. So we have all of that. So we have the next step, which is step 4, where it all comes to an end. We have step 4, which brings in another approach into this. So in step 4, we have a Lyapunov function approach. Lyapunov function approach to stability. So for Lyapunov function approach, right? Since this is a new concept, let's see a bit of introduction into this idea. Okay. Okay. So, or in fact, let me even make it into a whole topic on its own, a whole idea on its own. So, Lyapunov. Okay, I mean, well, I guess let's stop this here, right? So I can do Lyapunov function in another video, because this is already long. Okay, so let me see if I can have some practice questions, for this. Okay, yeah, I think we are good to go as far as this is concerned. So I'm going to talk about Lyapunov function and stability in another video so that we can take proper care of that. Yes, let me see if I can have some practice. Just drop one or two questions here. So, of course, you know the normal things we do. You find the equilibrium point of the system and compute the Jacobian matrix and determine the stability of the equilibrium point by analyzing the eigenvalues for 1 dx dt equals x into 2 minus x minus y. Then dy dt equals y into 3 minus x minus y. Okay, you find equilibrium points, you compute the Jacobian matrix, and determine the stability of the equilibrium point by analyzing the eigenvalues. So number two, margin number two, you have the x dt equals x into 2 minus x squared minus y, and the y dt is equal to y into 3 minus x minus y squared. Okay, number three, you have okay, a case of a chemical reaction, right? Consider the chemical reaction, the A, the T equals minus K1A plus K2B, and the B, the T equals K1A minus K2B. Okay, where A and B are concentrations of two reactants and K1 and K2 are positive constants. So you're going to do the normal things. Find the equilibrium point of the system, linearize the system around the equilibrium point, and determine the stability of the equilibrium point. So in the next video, I'll be talking about Lyapunov function and stability. So if you have not subscribed to this channel, please go ahead and subscribe. And if you have subscribed, don't forget to hit the notification bell so you can always get alerted each time a new video is released. Also, like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.